Okay, so we are now recording part 2 of lecture 3. So are there further questions that were being discussed in the break?
Please, please, in my thinking again, from what you described, that means that the intensity has nothing to do with the frequencies.
Yes, from the classical theory, this is not true. So the intensity is not related to the frequency. So you can change intensity and keep the frequency constant. Okay. Um, I think these kind of questions, for instance, someone sent in the chat, John sent in the chat, how do I determine the number of photons in a light intensity? So we are going to do exercises that will fix, this type of reasoning behind that, because it's just very difficult to explain these without a concrete example. But we're going to do examples, okay? Okay. Further questions? Okay, so I will continue with the material, and I will provide some exercise sheet for you to work on, and these will have exercises on the photoelectric effect. And I hope that you're going to, understand all these details at the practical level. But you already have these two exercises. So exercise 1 on page 13 and exercise 2 on page 14 that I strongly suggest that you try to do, and we can discuss that. Okay? So there is another question. Silas asked, suppose I want to eject 10 electrons from the plate. So I need incident energy equivalent to the sum of the individual work function. You see, the work function is related to the material and not to the electrons. So what you can do is the following. The photoelectric equation is the photoelectric equation. This equation here is about just a single electron. So you can calculate what is the energy that the fastest electron will have. So you can compute the kinetic energy by knowing these informations, namely the frequency and the work function. Okay? We are going to get to practical example. So this is not an assignment. This is just practice. So just I encourage you to try to solve these exercises, and tomorrow we can speak about them if you want. But I'm going to give to you an exercise sheet as an assignment. Okay. Okay. Let me continue with the lecture, and then we can discuss further about the photoelectric effect. So far we have discussed about the black body radiation problem that Planck solved by postulating that energy exchange was done via the exchange of quanta of energy. And we also talked about the photoelectric effect and how Einstein explained it by considering that light is a beam of photons. Okay? So those results, they give support to the picture of light being composed of particles. Okay. Now I'm going to discuss another phenomenon that is due to Arthur Compton, um, that also used the picture of light as a beam of particles to describe a very interesting phenomenon. So you see that we started these lectures talking about 1900, then we moved to 1905, and now I'm going to move to 1919. So, and actually it was until 1923, uh, the period that Compton did his experiments. So essentially, his experiments gave uh, uh, another source of confirmation that light behaves as a beam of particles sometimes. And what he did was to throw X-rays. X-rays are just radiation, and he threw X-rays against a target. So there is a target made of some material that you know about, and I'm just throwing radiation to this material. And in fact, what happened was the following. So he used X-rays which have a wavelength of zero 0.7 angstrom. So just to remind you what angstrom means is 10 to the minus 10. So the wavelength of the X-rays is of 0.7 times 10 to the minus 10 meters. And when you throw, just think about light as being now a beam of particles. You throw a beam of particles against a target. So these particles will hit the target and will be scattered, okay? So this is what's going to happen. You throw, there is a target here, you throw a particle, this particle will, for instance, go up, and this particle will go down. So it's something like a collision, right? And what happens was the following. So Compton analyzed the spectrum of this scattered light. Sorry, this is scattered radiation. So radiation was going up, going down, and so on. And he analyzed what would be the wavelength of the scattered X-rays. Okay, so I throw some X-ray with a given wavelength. It hits a target, and after hitting the target, it is scattered. And now I'm just going to measure what is the wavelength of the scattered X-ray. Okay. So what he found was that there was a component in some direction that had essentially the same wavelength of the initial X-ray. So if you had lambda 0, lambda naught as your initial wavelength, then there was at least in one direction that Compton could see a a wavelength that was also lambda naught. But also, what happened was that measuring in different directions the wavelength of the scattered X-rays, Compton realized that he could measure different values for the wavelength. And these different values were such that lambda, which is the wavelength of the X-ray scattered to a different direction, was bigger than the initial wavelength. So you throw X-ray, this thing scatters, goes up. You measure the wavelength of this X-ray that was scattered, and you see that the wavelength is bigger than the wavelength, the initial wavelength. And if you change the angle now, if you look at the scattered X-ray in a different direction, you see that lambda will change again. So for different choices of angle of the direction that you're making the measurement, you get different values of lambda. Okay? So you can now compute the following. You take the value of the wavelength that you are measuring in a given direction, and you subtract from the initial value of the wavelength that you used in the initial X-ray. So this is lambda minus lambda naught. This is called delta lambda, and this is what we call Compton shift. Okay, so what Compton wanted to do was to find a mathematical expression for delta lambda in terms of the scattering angle. Okay, so he wanted to derive an expression for delta lambda such that it agreed with the experiments. Okay. So in order to explain, or in order to derive an expression for delta lambda, Compton did what I said before. He took seriously what Einstein said, that light was made like a beam of photons. And for lambda naught being 0.7 angstrom, so the X-ray, the initial X-ray having this wavelength, the associated frequency, you have to remember that frequency and wavelength are related. We saw that yesterday. I can compute the initial frequency, and this is given by 3/7 times 10 to the 18, 1/2. And the energy of the incident X-rays, namely the energy of a photon, is just the product of this frequency with Planck's constant. And this gives to you approximately 18 kilo electron volts. So if you think about electromagnetic radiation, it will transport not only energy, but also momentum. So you have heard about momentum in elementary physics courses. So a particle that has a velocity, it carries momentum. So a particle, when it's moving, has kinetic energy, and also it has momentum, which is the product of the mass of the particle with the velocity of the particle. So photons, if you think about them as particles, they carry energy that you have learned. It's given by 8 times nu, but they also carry momentum, okay? So the initial momentum of the X-rays that are thrown against the target is given by this expression here. So it's given by the energy of the photon divided by the speed of light. So I'm not sure if you already encountered this expression in the relativity course that you're having before, but if you didn't, you are going to learn that, so don't be afraid. I'm just telling you that a photon will carry energy of h nu and carry momentum that is the energy divided by the speed of light. And this u naught hat is just a vector that gives to you the direction of the motion of this photon. Okay? So if we go now to the next slide, there is a picture of what I'm trying to describe here. Okay? So I have a photon that is traveling from the left to the right. And let's assume that my target is just an electron. Okay? So this photon that is coming by, it has energy E gamma naught and momentum P gamma naught. And the direction that it moves is the direction of this vector U naught. Okay? So just thinking as in classical mechanics, when I throw a particle against another particle, there is a collision and they will scatter. So in this particular case, the photon is going up and the electron is going down. But now the photon is escaping to this direction. So you see that the direction of motion of the electron has changed. It's not this direction anymore, but now it's going to with this angle theta. And the photon now has a different value of energy and momentum because it exchanged energy and momentum with the electron. Okay? On the other hand, the electron is going down. It was deviated by an angle phi with respect to the direction of u naught. And it has a value of energy that I call E and a momentum that is the vector P. Okay? So this is essentially the sketch of what I was describing before. Now coming back to the momentum of the photon, I said that the momentum is the energy divided by c. So if I want to compute the absolute value of the momentum, this is h nu, which is the energy, divided by c. And we have learned that the frequency and the wavelength are related by the velocity. So I can just replace nu naught over c by lambda naught. So the magnitude of the initial momentum of the photon is nothing but Planck's constant divided by the wavelength of the photon. Okay? Now I will just explain a bit more. As I told you, so this is the picture that I have. Compton wanted to measure, so you see now that the photon had initially a wavelength lambda naught. Now it is scattered and goes up, and it has a new value of energy and a new value of P, of the momentum. Since the momentum of the photon is related to its wavelength, then because of the momentum has changed, the wavelength of the photon will also change. So if I measure the wavelength of the photon here after the scattering, I can expect that it will be different from the initial wavelength here. Okay? And now comes the conclusion. So I didn't want to derive the expression here because it requires a knowledge that I don't know if you already had from the relativity course, which is the conservation of energy and momentum. I don't know if you learned that in the previous lectures, which is the conservation of energy and momentum in special relativity. Did you? Okay.
No.
Okay, thank you. So it's good that I didn't wrote the entire derivation because I mean this would be I can write that for you and you can read about that in the future when you learn the conservation laws in relativity. Okay. So if you apply the conservation laws in relativity of energy and momentum, so in classical mechanics, we know that energy and momentum are conserved quantities under some assumptions. In relativity, this also happens. So in relativity, energy and momentum are also conserved. So if in this collision you apply the conservation laws, you can derive an expression for delta lambda, namely for the Compton shift. And the expression is given by this factor here, so the Planck's constant, divided by the mass of the electron times the velocity of the speed of light, times this factor, which is 1 minus the cosine of this angle here. So you see that if I change the angle, if I change the angle that I will detect the scattered photon, I will change the value of lambda, of delta lambda, sorry. Okay? In particular, if theta is 0, cosine of theta, how much is cosine of 0? 1. So 1 minus 1 will give you 0, and delta lambda will be 0. So if theta is 0, it means that the photon will just continue moving through the electron. And you can say, well, but this is, the electron should move a little bit and the photon as well. But you can think about the following. If let me explain this first. So this quantity h divided by the mass of the electron times the speed of light is what is called the Compton wavelength. So this just depends on universal constants. So it depends on the Planck's constant, the mass of the electron, and the speed of light. So I can compute this once for all, and this gives 2.426 times 10 to the minus 12 meters. And what Compton managed to show was that this expression that he derived from the conservation laws of relativity, and also assuming that light was made as a beam of photons, was in very good agreement with experiments. So again, treating light as a beam of particles is giving the correct answers for experimental data when light interacts with something else. Okay? So there is a question in the chat. Every wavelength has a specific scattering angle. So in a sense, what this expression says to you is that depending on the direction that you are looking at, so depending on the angle that you are looking at, you are going to see different wavelengths. You are correct, Mahmoud. Why are we using the mass of the electron? I think we are, yes. So the mass of the electron enters the game because, I didn't explain that, but what Compton did was to scatter photons with a material, with a target that was carbon-based. And for carbon-based materials, you see that the energy of the incident photon is way bigger than the binding energy, namely the work function. So you can simply disregard the binding energy and just consider the target as being just a single electron at rest. Okay.
Hello.
Yes, go ahead, please.
Yeah. In Compton scattering, is this all this process happen inside the material, or the electron leaves the target, and this scattering happen outside the material?
Yeah. So this energy of the incident X-rays is sufficient to remove the electron from the material. Yes.
Okay, that means the detection happen. Okay, thank you.
Okay. Uh, So there are more questions. Why are we using the mass of the electron? Yeah, so I was answering to that. So because we can use, because Compton was using this carbon-based material, we can treat the electron as a free particle at rest, and therefore I can just assume that the target is just a single electron. And if you work out the conservation laws of relativity, you are going to get this factor that depends on the mass of the target. Okay? So, John, for your question, you can view that as just a collision. So if just think about this is a ball and you kick another ball into the direction of this ball. When this ball that you kicked hit this ball at rest, they will scatter, right? So one will go to this direction and the other will go to this direction. So just think of these as this classical collision of particles. Okay? Okay, so you see that if I look at angles that are very close to zero, okay, I will get a Compton shift that is very close to zero. In particular, if I look at radiation that is emitted in this direction here, theta equals to zero, I will find that the Compton shift is zero. Okay? So treating light as a beam of particle is again a very good description of the outcomes of experiments. Okay. Yeah, so there is this question, elastic or inelastic collision. Yeah, so there is this distinction. So there are collisions. So in collisions, you always conserve momentum, but you just conserve energy if the collision is elastic. So I'm assuming here an elastic collision, okay? So if you want to take into account dissipative effects, you have to be more careful because energy then is not conserved. Okay, that's a very good question. Okay. Okay, so now we have to discuss another topic, but I don't want to rush. So I don't want to do that in 4 minutes. But essentially, this is a very important discovery made by Rutherford, which was the following. Essentially, Rutherford discovered that the atoms had a nucleus, okay? And people were aware about the existence of electrons, but they didn't know that the atom was formed by a cloud of electrons and a nucleus, a tiny nucleus, and the electrons were flying around this nucleus. And this is very important because we are going to discuss the first, let's say, realistic in a sense. I don't want to use this word because it seems that the others were not realistic. Well, they were made with the knowledge that people had at that time. But there is a model, an atomic model, due to a physicist, a Danish physicist called Niels Bohr, that was extremely important for the development of quantum mechanics. And the crucial question that made Bohr to consider this model was the following. So Rutherford discovered that the atom is made of a nucleus with positive charge and a cloud of electrons. Okay? We know that electric charges of different signs, namely positive and negative charges, they try to attract each other, right? So I can think of the nucleus trying to attract the electrons closer. And then you can say, well, why this doesn't happen? Why electrons move at some given orbits around the nucleus if there is a force that tries to bring them towards the nucleus. And we are going to see that it is very important that classical dynamics is changed in order to explain that. And this is where quantum mechanics enters again. So the atomic model by Bohr will be very important for the birth of quantum mechanics. But before that, we're going to discuss Rutherford, and this I will do tomorrow. In fact, we have to discuss Rutherford, then the atomic spectra, the Bohr atomic model, and then we are going to discuss waves of matter, which is very important. And then after that, we will be done with the old, let's say, quantum mechanics, and we can move to the modern quantum mechanics, and we're going to learn the modern formulation of quantum mechanics. Okay, are there questions? So if this is not the case, I thank you for your attention, and I invite you to look at these exercises on page 13 and 14, and you can send me emails with questions, of course. Okay, so very soonish I will post the video in the YouTube channel, and I will send you the link, and also post the PDF of the lecture notes in the course, in the lectures website. Okay, so thank you very much. See you tomorrow.